In our final video here for section 6.2, we are going to address some rational number properties and then look at approximations in mental calculations. I'm going to go fairly quickly through the rational number properties because we've seen these properties before, but it is important to revisit them. And anytime we're introduced to new number types, it's important to consider whether the properties that we've used before hold for this new type of number. And so the first one we'll talk about is closure. Remember, closure means if you do an operation to these numbers, do you get an answer that is still one of these types of numbers? And the set of irrational numbers, remember what a rational number is, it's any number that can be written as a over b so long as b does not equal 0. So it's something that can be written as a fraction. Those are closed under both addition and multiplication. So if you add rational numbers, you'll get a rational number back. If you multiply rational numbers, you'll get a rational number back. Commutative. Rational numbers are commutative for both addition and multiplication, meaning you can change the order and you'll still get the same answer either way. A couple other properties that we looked at before, which hold for rational numbers, are the associative property. Remember, associate means who do you want to associate with? If you're this middle number, A, B, and C, do you want to get added to A or do you want to get added to C? Right? So you can add A plus B or B plus C and then add the other number and it's still going to be the same. That's true for both addition and also multiplication. So rational numbers are associative. And then we have identity. Remember, identity is who you are as a number. We have two different types of identity properties. One is for addition, and that is 0. If you add 0, you stay the same. You didn't change the number. For multiplication, that number is 1. Multiplying a rational number by 1 gives you that same rational number. So those are the identity properties. We also have inverse properties. Those exist for rational numbers as well. For every rational number, there is a unique inverse for addition, and for every non-zero rational number, there's a unique inverse for multiplication, right? So it's the opposite with addition. For any rational number, it's its opposite, the negative version, that when you add it equals 0. Remember, inverses, when you add them, equals 0, and inverses, when you multiply them, are equal to 1. So the inverse multiplication is when you take the reciprocal, right? So if you have some rational number C, its inverse is 1 over C. And when you multiply, it changed to that arrow again. And when you multiply those, you'll always get 1. So rational numbers have inverses. And then the distributive property. We love the distributive property, multiplication over addition. A times B, A times C, and add them is the same as doing A times the sum of B and C. So all of those properties do hold for rational numbers as well. So those were not new, but I just wanted to make sure we talked about them for rational numbers. Let's move on and talk about some mental computations. This is such good practice for you, right? It's building your math brain a little bit. So we've done this with whole numbers, we've done it with fractions, and so we're going to use some of these same techniques to do operations with decimals as well. So the first thing we're going to do is look at just a couple different mental problems we could do mentally with decimals. So let's say we had 0.44 times 0.22, 22 hundredths. You should be able to do this fairly quickly in your head by just multiplying the decimals as if they were whole numbers first. 4 times 22 is 88. Then once you've done that, then you figure out where does the decimal point need to go, and you can reason through that. But we also know that when we multiply we count the number of decimal places, and we have to have that many in our answer. The only way for that to happen here is if we put a 0 in front of that 88, and then we have our 1, 2, 3 decimal places. In a problem like this, 0.35 plus 0.55, now we have addition. Again, that should be something we can add in our head just by starting with 35 plus 55. In my head, I always start with, especially when we've got those ending in fives, I know they're going to add to be a nice, neat 10. So 30 plus 50 is 80, plus another 10 is equal to 90. And because these were both in the tenths place, that's going to be in the tenths place, and we end up with 0.90 or 90 hundredths. So try a couple of these on your own. 5 times 3 thousandths, 345 thousandths minus 2 tenths. And let's do 24 hundredths divided by 4 hundredths. Go ahead and give those a shot. For the first one, we're multiplying. And so I know that 5 times 3 is 15. If I just think about 5 and 3, it's 15. Consider, where does that decimal point have to go? Again, 1, 2, 3 decimal places. 1, 2, 3 would require that 0, and we have 0.015. Here, 345. Careful with this one. It might be helpful if you imagine this as 200. 345 minus 200, because then we're subtracting thousandths from thousandths, is 145. And my decimal point will go in front of that 1, because we started with thousandths, 3 decimal places, we ended with 3, and so that's going to line up right where it would in front of those tenths places. This is an interesting one. 24 hundredths divided by 4 hundredths. 24 divided by 4, I know, is 6. Is that going to be our answer? If you remember from working with long division of decimals, we never divided by a decimal. We always moved it 2 spots, or we moved it to the end. Well, if we move that 2 spots and that 2 spots, we actually end up with 24 divided by 4, which is 6. Again, whatever you're dividing by, you want that to be a whole number. So those are just a few ways to start this process of mental calculations. Let's look at some other more specific strategies. One of the strategies we looked at before was what we called the add-up strategy. And this was specifically when we were dealing with subtraction. And so imagine you have to do this calculation in your head. And I challenge you to try 0.54 minus 0.38. Now, I don't know how you all picture things. My brain likes to imagine these things stacked vertically. So I imagine in my head 0 here and 0.38 here and 0.54 here. And we're starting at 0.38. So we've already started here. This is our like our baseline. And then we're subtracting 0.38. Again, you can also think of it as that add up concept. We're trying to find the distance it would take to get from here up to there. And that's going to be my answer, right? And so you can do this in phases. The first thing that you might do if you're trying to use the add up technique is get this 0.38 up to a nice number. A multiple of 10 is always good. So if we add 0.02 to 0.38, that gets us up to 0.40. From there, if you think about this as 40, and we're trying to get to 54, we have to go another plus 0.14, 14 hundredths. So again, if we add 2 hundredths it gets us from 0.38 up to 0.4. And then if we add 14 more hundredths, it gets us from 0.4 or 0.40 up to 0.54. And so by doing these two consecutive addition problems and then combining their answer, we get 0.16 or 16 hundredths. That's our answer. That is the difference between 54 hundredths and 38 hundredths. So again, this isn't always pretty, as you can see by my diagram here. But this is the thinking you can train yourself to do. Again, how do I get from here up to a nice neat number? And then how do I get from there up to my answer? You can even do it in more phases than that. This is just one approach. Another thing you can do is what we call substitution. Substitution. And so imagine you have to do 4 times 99 hundredths. One way you can do this is through the substitution method, where you replace 0.99 or 99 hundredths with 1.00 minus 0.01. 1 and 0 hundredths minus 1 hundredth. 1 minus, imagine it is money, $1 minus a penny is 99 cents. And so this is equivalent to 99 hundredths. Then you distribute 4 times 1 is 4, or 4.00, minus 4 times 0.01 is 0.04. If you think about it in terms of money, it's $4 minus 4 cents. And that is something you can maybe do in your head. Say we're left with 3. Now, you might not picture all this work in your head. I certainly don't. I just say in my head, I know that 99 is really close to 1. So 4 times 1 is 4. But I've got to subtract that difference, right? How much extra did I add? 0.01, and I have to subtract 4 of those. There's that 0.04 that we're subtracting. So mental math isn't always neat in your head. It can be a little bit messy, but this is what's happening behind the scenes when you're doing those. So why don't you go ahead and try a few of these using any of these techniques that we talked about so far. We will do these 3 problems. Give these each a shot. So for that first one, this is a subtraction problem. So that add up technique might work really well. And so however you jot your notes down when you're doing this, and again, ideally you're doing this in your head, I'm taking my 0.29 and I'm first adding 1/100th to it to get up to 0.30. That gets me to 0.30. And then from 0.30 to 0.76, I've got to add 0.46. The 4 gets me up to a 7, and then the 6 gets me up to that 6. So I've added 1/100th and 46 hundredths. Together, that's 47 hundredths, and that's going to be your difference. Okay, so you can start to see how this technique can be used. 3 times 0.98. This could be thought of as 3 times 1 minus 0.02, which is equal to 3 times, or I'm sorry, 3 minus 0.06. If you think about it in terms of money, again, we're multiplying 3 times 98 cents. Well, that's 3 times 1 minus 2 cents, which is 3 minus 6 cents, which is $2.94, or 2 and 94 hundredths. This one, I would say, separate the 102 and do 4 3/10 times 100 plus 2. 4.3 times 100, you should remember this, is 430 plus 4.3 times 2 is 8.6. And then we get 438.6. So again, this is not always the easiest thing, What I care is that you know these techniques exist, and then maybe you could explain how to do it to somebody, how to do these mental calculations. It doesn't mean you're always great at it, but you can explain it. So another technique we used was what we called equal quotients. This is specifically when you are dividing. Equal quotients. And what this really comes down to is when you're doing a division problem, if you think about a fraction as being a division problem, we can multiply both numbers by the same factor, and it keeps the problem equivalent. It keeps our fraction equivalent. That's the technique we can use if we're doing a mental calculation such as this. 21 hundredths divided by 2.5. Now you might look at that and say, there's no way that I could do that mentally. Well, let me show you. If we can get one of our numbers, specifically our divisor, into be a nice, neat power of 10, then our division becomes much, much easier. If you take 2.5 and multiply it by 4, it turns into 10. If you then do that same multiplication to 0.21, you have 0.84. And that works the same way that this keeps our fraction equivalent. When you're dividing two numbers, you can multiply both numbers by the same thing, and the problem will still work out the same way. 0.84 divided by 10, you then know to move that decimal one spot to the left to get 0.084. So again, noticing that this turns into 10 by multiplying by 4 allows you to then do the same thing here and then do that division by 10. So it's your turn to try these. Try 0.34 divided by 50 and try 0.16 divided by 200. Again, challenge yourself to do these in your head first. In both of these cases, you were dividing by numbers that could easily be turned into 100 by doing one simple move. For the first one, we're doubling it. If we double both of those numbers, we now have 0.68 divided by 100. And when you divide by 100, you're shifting your decimal point 2 places to the left, 0.0068. For this one, we're dividing by 200, so we can divide both of these by 2. It's the same thing as multiplying by 1/2 if you'd rather have it as multiplication. That changes our problem to 0.08 divided by 100. And then when we move our decimal point 2 spots to the left, we get 0.0008. So equal quotients is a really nice technique, especially when we start to deal with numbers that can easily be changed into 1,000 or 100 or 10 or some power of 10. Now, sometimes when we're doing mental math, mental computations, it's helpful to know some common fractions and their decimal equivalents. And so what I have here are some common ones that can help us. It would be good for you if you committed these to memory. These help with many, many mental computations. 0.25 is a fourth, 0.5 is a half, 0.75 is 3/4. 0.2 is 1/5. 0.4 is 2/5, 0.6 is 3/5, 0.8 is 4/5, 0.125 is 1/8. So those are good fractions to know and be aware of, because then you can do some substitutions, which may make certain calculations easier. Here's an example. Imagine you have to multiply 0.25 times 800. Knowing that 0.25 is equal to 1/4 allows you to consider this instead, 1/4 times 800. From there, you should, you could do this a couple different ways. You could think about it as 800 divided by 4, or you could even do some cancellation. 4 cancels with the 800 to be 200. In any case, you're doing 800 divided by 4, which is 200. Multiplying by 0.25 is the same thing as multiplying by a fourth or dividing by 4. One more that you may find helpful is this: 0.6 times 45. Now, again, that initially looks probably like something you wouldn't think you could do in your head. However, if you know that 0.6 is equal to 3/5, notice how there's some cancellation that can happen here. 45 and that 5 can cancel if we remove a factor of 5 from both of them. And all you end up with here now is 3 times 9, which is 27. So 0.6 or 6/10 times 45 is equal to 27. But we did that nothing like we would normally do decimal multiplication. We substituted in an equal fraction and did some canceling. Sometimes fractions are actually easier to use than decimals. And so let's try a few more of these. Let's try 0.125 times 24. I'll have you do this one. And also try 0.75 times 12. And try 0.2 times 30. See if you can go back to those decimal and fraction equivalents and do these in your head. And even if you aren't able to do them in your head, see if you can at least do the substitutions and attempt them in a different way. If you recall from before, 0.125 is equal to 1/8. And as soon as I replace that 1/8, maybe you're already starting to notice something. 1/8 times 24 is the same thing as 24 divided by 8. Or maybe you're thinking about it in terms of cancellation. 8 and 24 cancels to be 3. 1 times 3 is 3. And that's it. 0.75 as a fraction is 3/4 times 12. Maybe you notice that there's some cancellation that occurs here. 4 and 12 cancel to be 1 and 3. And 3 times 3 is 9. For this one, 0.2, do you remember the fraction equivalent for that? It's 1/5. 1/5 times 30. Well, it's the same thing as 30 divided by 5, which is equal to 6. And so there we saw, again, using fraction equivalents to do these mental calculations. So let's move on from mental calculations to approximations. And they have some similar thoughts, some similar ideas. Sometimes we just need to get close enough. And we've looked at rounding, we've looked at front-end approximation, we've looked at compatible numbers as ways that we can do approximations. Because again, sometimes you just need to make a quick decision, and close approximation is going to get you close enough. Here is a scenario that you're going to consider. And you're going to see if you can just do this approximately. So you're interested in the total cost of a home entertainment system with the following components, and see if you can do this by approximating the value by rounding each of them to the nearest $100, and maybe even attempt it in your head. Maybe try it mentally. Whether or not you were able to do it mentally, you probably came up with something that looked like this. 129.99 is rounds to 100. If we round to the nearest 100, I've got a typo in there. That should be 249. 249.50. Actually, you know what? I'm just going to change it right in here. Let's change you to 230. It doesn't matter. It's still going to round to $200. 579. Again, I changed these. I meant to change those numbers. I'm going to leave you as 4. We're just going to delete that, and we're going to approach this differently. I'm going to fix that in the slides. So if we round them to the nearest 100, the streaming device would round to 100. The soundbar would round to 200. The TV would round to 500. The gaming controller would round to 100. When we add all those up, 3, 4, that rounds to approximately $900. So that is, again, a way to do a quick rounding to just get that approximation. Sometimes that's all we need to do to make our decision. Whether it's 900 or 1,000, right, may not matter. You're just trying to get an approximation. Now, why is this so important? I don't think enough attention is paid to approximations because according to the National Council of Teachers of Mathematics, this strategy, this tool, is an important companion to computation. They are not mutually exclusive. They go together. It provides a great tool for judging the reasonableness of some calculation, right? Whether it's mental, whether it's paper and pencil, you always need to be able to know if your answer makes sense. And approximations are so important in doing that. Let's look at this in terms of some decimal numbers. So if we want to do 1.7 times 3.2, we may round both of those numbers to the nearest whole number. So this would be approximately 2 times 3. So we know this is going to be approximately, if I make my squiggly equal signs, 6. I think it's also important that we consider what that looks like. And so here is a visual of how our rounding affected the actual answer. And so across the top, we have 1, 2, 3.2. So this number 3.2 is illustrated across the top of our diagram. 1.7 is illustrated along the side. And when we rounded, what we did was we changed 3.2 into 3, which is essentially eliminating all of this stuff. When we rounded 1.7 up to 2, we then added on this. So you can even see from the diagram that we added on a little bit more than we took away. And so our answer is probably going to be a little bit bigger than the actual product. But that's okay, because we're just going for, again, an approximation here. So let's practice this by rounding to the nearest whole numbers. So we will do 4.6 times 8.21, and we will do 10.263 times 5.9. So go ahead and do those approximations just by rounding to the nearest whole number for both of them. For number 1, this is going to round to 5 times 8, which is approximately 40. So right there, again, this tenths place will round that 4 up to a 5. This tenths place will round that 8 just down to 8. For number 2, this will round to 10 times 6, which is approximately 60. So sometimes we round both numbers to the nearest whole number. Now, one thing that a lot of you found interesting in the discussion boards from earlier in the semester was this idea of front-end approximation. A lot of you said you had never seen this or never considered it. True, front-end approximation is generally going to be less accurate than rounding to some other number, but sometimes it's just the easiest thing to do in your head. So if you have 762 times 0.26, and you want to quickly just find out what is this, rounding it to the first digits, 700 times 0.2, allows you to kind of quickly see that this is going to be about 140. 2 times 7 is 14. 2 times 700 is 1400. And you know you're going to have that one decimal place, which would be here. You don't need it. So you can say that that is really close to 140. Again, we rounded both numbers down, so this number is going to be lower than the actual amount, but if you're just trying to get in the ballpark, it's a really nice strategy. So I'll just have you do a couple of those. Again, we've seen this strategy before, so go ahead and try using front-end approximation, 0.328 plus 0.511, and 2.6 divided by 0.53. I'll give you a moment to do that. Again, if we're just using front-end approximation, we're rounding just the first digit, right? We don't even round. It's not even rounding. You're just using the first digit. 0.3 plus 0.5 is approximately 0.8. Okay? Again, your answers are always going to be lower when you're using front end, but it gets you in the ballpark. For number 2, 2 divided by 0.5, the same thing as 2 divided by a half, which is equal to 4. And so again, you can at least get something close. The last strategy we'll look at, again, we've seen this before, it is compatible numbers. So this is a little bit looser of a rule. It's not even a rule, it's a technique, but it's up to you to be the judge of how you think you should round it. It's not just doing front end or just doing to the nearest whole number or to the nearest tenth. It's you saying what numbers could fit well together or work well together in this scenario. So I think this is the most useful, and it's one I probably use the most. Here's one example, 3.71 plus 0.24. If you need to add those numbers, you could do a little bit of rounding and say, well, I could round this down to 0.37 and this up to 0.3. And I chose those numbers because 3 and 7 here make 10. And I know that will then round up or add up to 4, exactly 4. So I'm going to give you a few of these to try as well. 6 different problems. And so I'm just going to paste this whole slide right here. And you're going to look for compatible numbers to answer each one of these questions. Now, the thing about compatible numbers, when you're approximating, you might do it differently than me. What you saw as compatible might not be what I saw as compatible. And so I'm going to go through how I saw each of these problems. For number 1, I rounded this to 6 divided by 0.3 because I knew 3 divides evenly into 6. That answer will be 20. 6 divided by 3 is 2, and I had this extra decimal point, so I've got to move that decimal one more to give me 20. Or another way you could have thought about that is 60 divided by 3, because remember, we never divide by a decimal when we're doing long division. So if you did that strategy of equal quotients, that also shows you why it turns into 20. For number 2, I saw 1.5 minus 0.5. I just rounded this up to 0.5, and that's going to equal 1. For number 3, what I saw there was 0.4 times 250. This is kind of close to 0.4, and this is kind of close to 250. Now, why did I do that? Because I know that 4 times 250 is 1,000. 0.4 is going to have a decimal here, which means it's going to be equal to 100. For number 4, what I saw was 2.85 plus 5.15. Now, maybe this is one where we differed on our approaches. For me, I obviously work with numbers all the time, so I recognize immediately that 85 plus 15 is 100. Maybe that's not something that jumped out to you. So when you add those, the 2 plus the 5 is 7, and the decimal portions add up to another 1 whole, which is going to be 8. Perhaps you just rounded it to 3 plus 5. That also works. For number 5, what did I do? 0.2 times 50. 0.2 times 50, well, I know 2 times 50 is 100, so 0.2 times 50 has to be 10 times less than that. 10. And then finally, number 6, I did 27.8 minus 1.8. Those decimal places there, just make them the same. And then I take away the 0.8 and I take away 1, and I'm left with 26. So again, I think it's really important that we know that there's no one perfect way to do those. You're just looking for numbers that work well together for whatever operation it is that you are doing.